Hi, everyone. So I want to take you through the second task of JMol because it seems like not everyone, but a lot of people are having some problems, and I want to make sure you guys get this. Okay, so what you can do is go to the PDB and you download this file, 1PGB. Or if you're using Proteopedia, you just type in 1PGB and the image will pop up. In Protopedia, make sure you click on that yellow button that says load full so you get the full structure in there. Okay. I'm working off of JMol right now. This way I can save the image to my computer. So here's our protein. It's in ribbon view, and ribbon view, again, just lets you see what the major structures that are secondary structures, what they look like. So again, we've got some beta sheets here. Beta sheets are always colored yellow, and they always have these arrows showing their orientation. Okay, and then we've got this alpha helix in here. And the white stuff is just protein that has no secondary or tertiary structure, but it's looped, and they've identified its structure as far as where it's located. So this is a 56 amino acid residue portion of a bigger protein, which is called the immunoglobulin binding domain of streptococcal protein G. Bleh. Okay, basically it's a part of a protein. So you got the cartoon view up already, but what we want to first do is get rid of the water. So we're going to delete water. Okay, and you'll see that those little red spheres disappear. Okay, so we've gotten rid of the water. And now we want to show structure, okay, just to see what information is displayed. So that tells us what we've got here, that we have 56 amino acids. We have a helix, which consists of alanine 23 to aspartic acid 36. We have 4 beta sheets. Sheet 1 is methionine A to glycine A9. A refers to it's the A structure. We have a leucine 12 to alanine 20 for number 2. Sheet number 3 is 42 to 46, and 4 is 50 to 56. Okay, so that's the sequence in which the sheets occur. And what you'll notice is there's a gap here between 20 and 42, and that's where that helix pops in there in the middle. Okay, and so you can kind of see the orientations. If we look, the arrows point in the ascending direction. So it looks like, yep, we're starting here. Sheet 1 is over here somewhere. Is sheet 1, 2, 3, 4. Okay, and then here's our helix. Okay, and so notice the beta sheet is curved, right? And it's got this kind of convex appearance to it. Okay, but this is just showing you the ribbon. Okay, so now we're going to go into backbone. So to go into backbone display, and by the way, I'm just going right along with this. Okay, so we're going to go into backbone display, and when we do this, we're going to type in backbone 100. Okay, now the cartoon's still on, so we have to get rid of that. So you type cartoon off. Okay. Now the cartoon is off. Okay, and you can see now that we're just looking at the carbon backbone. And now we can actually see the orientation of our helix. I'm not sure which end is the beginning because I can't tell right now. But if you click on the ends of the protein, we can identify the N and the C terminus. Okay, so if we click here, oh look, that's met 1, so that's the beginning. That's number 1. And then this is the end, should be number 56. And it is. Okay. Another way to figure out what we're looking at is if we click on color group. Okay. And this is kind of cool. This gives you like a rainbow appearance. But basically what it does is this allows you to see where the beginning of your protein is. You guys remember, I know one class we did this. We did the tubers. Blue is the nitrogen end. So this is the beginning. Blue is the beginning, and red is the end where we stop. And so if you look at this in this rainbow orientation, this shows you exactly where the beginning and end of your protein is. And you can kind of follow the sequence to know that, okay, you're starting here at the beginning, we're getting a little further away, okay, and then we're getting closer to the end. It starts to warm up the colors, and then we get to red at the very end, okay? You can do this with every protein to figure out where the beginning and the end of the protein is, okay? And so we can then go back to color structure. Okay, and now we're back to the way it was. Okay, so now what do they want us to do? All right, describe the order of the various secondary elements as they occur in the primary sequence. So we know that residues 1 through 9 are in a beta sheet. Okay, so that's 1 through 9. Here's 10 and 11, they're in a turn. And then 12 through 20 are in another beta sheet. Okay, and then this is number 21 and 22, they're in a turn. And we know from this that numbers 23 through 36 are in an alpha helix. Okay, and then we have a bunch of white ones here. Now, to figure out the numbers, click on the elbow or the bend of each of these. So if I want to know what this one is, I could zoom in. That's number 37. That's number 38, 39, 40. Okay, 41. And now we go right into another helix. Okay, I'm sorry, sheet, which is 42 to 30, 46. And then this should be number 47, 48, 49. And then the next sheet starts at number 50 and goes all the way to 56. Okay, so the way you would write this is residues 1 through 9 are in a beta sheet, 10 and 11 are in a turn, 12 through 20 are a beta sheet, 21 to 22 are a turn, 23 to 36 is a helix, 37 to 42 is a turn, 42 to 46 is a helix, I'm sorry, a sheet, and then 47 to 49 is a turn, and 50 to 56 is a sheet. And that's what you would describe, okay? So now we're going to look at the beta sheet. And so we want you to number the 4 regions so that we can see that we're dealing with, let me just spin this a bit. There we go. Okay, so I know that this is the beginning of this. So this is sheet 1. Okay, and then this is sheet number 2. And what's interesting is it's sheet number 3 is here, and then this is sheet number 4. So going in order from one edge of the beta sheet to the other edge of the beta sheet, it goes 2, 1, 4, 3. Okay, it's 2, 1, 4, 3. That's the order that we go. And that just shows you that beta sheets, they're going to alternate with each other sometimes so that they can form hydrogen bonds. Okay, and the hydrogen bonds are going to form where these elbows are. So you're going to have here, down here, up here, down here, up here, down here. So wherever there's a zigzag, that's where they're going to form their bonds. You see how the zigzags line up on a beta sheet? You can kind of follow it. So that's where they hydrogen bond with each other so they can form that sheet. Okay. So for these strands, they are running anti-parallel to each other. This is going in this direction. Then this is going in the opposite direction. This is ascending this way, ascending this way. And then this one's ascending this way and it's ascending that way. So they're running in opposite directions. So basically, if I could draw an arrow, I'd have an arrow pointing this direction, then this direction, then this direction, and this direction. And actually, if I do something real quick, you see how the arrows are pointing in opposite directions? This arrow is going this way, this arrow is going this way, and this one going this way, and this one's going this way. So these two are anti-parallel to each other, and these two are anti-parallel to each other. What's interesting is the ones in the middle are oriented in the same direction, so they're parallel because the numbers are increasing. This is 1 through 9, and this is 40, 50 to 56. So these are increasing in number, and these are increasing in number going this way. And the number I'm referring to is the number of the amino acid. Okay? All right, so let me undo what I just did. Okay, so next, now following the directions, I want to do H bonds, so we're going to do H bonds calculate. Okay. And this throws a whole bunch of hydrogen bonds in there. Just so you can tell, you see how the hydrogen bonds are going parallel, okay? And in the helix, you see how the H bonds move up and down, where these are side to side, okay? You'll see that a little bit more when we get them to show a little bit better, okay? So we're going to make these H bonds a little bit better. We're going to do H bonds 20. All right, they're a little bit thicker, okay, but we want to make them a different color. So we're going to do H bonds cyan. Cyan's a nice color to use. There we go, because it pops really nicely, okay? Sometimes they're hard to see against a black background, so you can make the background white or different colors, okay? But notice that they run perpendicular to the strands of the beta sheet, and they lie in the plane of the sheet, while in a helix, they're parallel to the axis of the helix. So the helix axis goes this way up and down. I'll make this big for a second. All right, here's our helix axis, okay, and these move up and down, and then these, the H bonds, are perpendicular, right? The sheet's going this way, the bonds are coming out from the sides. They stick out, okay? And again, the hydrogen bonds are what are holding those to each other so that you can form those particular strands, okay? Okay, so let's see if we can see other atoms. So what we're going to do is we're going to select all, and we're going to type wireframe only, and it looks like a big mess, right? Now we're going to set H bonds to the side chain, because the hydrogen bonds really come from the side chains, and what they're doing here is they're floating around in space, okay? But now we're going to set them to the side chain. You're going to see what happens. They're going to make a connection, right? So watch this. I'm going to hit enter, okay? And they're going to connect, and then we're going to connect it to the N and the O. And then what we're going to do is we're going to color H bond CPK. Okay? What that does is it shows us where there's a hydrogen, I'm sorry, a nitrogen end, which is the blue, and an oxygen end, which is the red. So this is showing us where there's a connection between an N and an O, okay? And it's the hydrogens between those that are connecting them, okay? That's what that indicates. And so first we're going to look at the beta sheet. So we're going to type in select sheet, and we're going to color CPK. So now just the sheet's being colored. If you notice, the helix is still magenta. Now we've colored sheet CPK. You know what I did? I did something wrong. Notice the difference between this image and this image. I forgot wireframe 100. So right now what I'm going to do is I'm going to do select all. I'm going to type wireframe 100. There we go. Now I'm a little more puffy looking, okay? And I can really see where those hydrogen bonds are connecting now, okay? They are directly connecting, okay? Okay, now I'm going to restrict sheet. So I took away helix. I'm restricting it to just looking at the sheet. I'm going to select not sheet. And here's what I want to do. I want to turn off hydrogen bonds that are floating around aimlessly. If you look, if I take this away, you can see where my helix is, right? The hydrogen bonds are there. I want to get rid of those. So I'm going to type in select not sheet, and I pick those, and then we're going to turn the hydrogen bonds off. Okay, and the way we do that is simply by typing H bonds off. Okay. Now we're just looking at the hydrogen bonds between the beta sheets. And you can see how they zigzag, okay? So when you zoom in, you can see how each H bond connects an NH group with an O, okay? and this is a carbon bound to an oxygen. This is a nitrogen bound to an H, and so this is where the hydrogen bonding is going on. Okay. You notice that the reds alternate up and down. Okay, that's how beta sheets work. Okay, if you notice on this side, it goes red, blue, red, blue, red, blue, red, blue. So they alternate up and down. Okay, you see how the blues here, reds here, blue, red, blue, red. Okay, and so they form a zigzag. Okay, and the reason for that is just naturally the way that they form this bond. Okay, so now we're going to look at the alpha helix. So we're going to select all. Okay, and we're going to do wireframe 100, color CPK. Okay, we're going to restrict helix. We're going to turn everything off except our helix, and then we're going to do H bonds 20, makes them a little thicker, and then we're going to do select not helix. So we're going to select anything that's not a helix, and we're going to turn those H bonds off. Okay, so now we can just look at exclusively this. Okay, and we can see the hydrogen bonding going on between the different components of the alpha helix. Okay, and if we go right down the middle of the helix, okay, we're peering down the center of the helix now, and we see all the side chains sticking off the side. Okay, if we go this way, now you can see the hydrogen bonds are in the plane of the helix. Okay, and if we look this way down this end, now we're looking from the top end down. Okay, and if we orient our helix this way, basically this looks like a big Christmas tree. I'm going to show you something. I'm going to do excuse me. Yep, live action here. Here we go. I want to undo this for a minute. Here's our backbone for the helix. Okay, I made this a little thicker, but I want you to see how if you look down the center of the helix, okay, it's a tiny little opening in there now, but this is showing you where the hydrogen bonds are in our helix. Okay, this is our backbone of the carbon, and then those are all the side chains that are sticking off the sides. You can really get a sense of this now of the hydrogen bonding that goes on in the helix. Okay, it's easier to see it this way. I wanted to show it to you guys this way. And then these are all the side chains sticking off. Okay, notice how this one doesn't have any red or blue. Okay, that's nonpolar. This is nonpolar. This is polar. It's got a little oxygen there. So if you don't see any red or blue, then you know that it's nonpolar. If you see red and blue, you know it's polar and possibly charged, possibly acidic or basic. Okay, all right. So I'm going to undo that so we can get back to the orientation that we need to be at. Okay. And now what we're going to do is we're going to select all. We're going to do H bonds 20. And we're going to do wireframe off. And this is just showing you the hydrogen bonds and how they appear. Okay. So you can actually pick out the hydrogen bonds in a helix because you can see how they're perpendicular to each other. And they're all moving, not perpendicular, they're parallel to each other, moving up and down. And when you look at your sheets, you see how they look flat? You can kind of see that there's almost a flat nature to this, okay? Where these are all oriented, and there's like groups of 3, okay? And if you took this and looked down the middle, here's your alpha helix, okay? And then look at your sheets, how flat they are when you look at them head on, okay? So that's just a neat little way that you can see all those hydrogen bonds in there. Now, why is this important? Because scientists like to see where the hydrogen bonding is because that tells them how the entire protein is operating, okay? So we can restore cartoon. So what we're going to do is we're going to type select all. We're going to do cartoon. We're going to do color structure. and rotate. Okay, and that's causing that thing to spin. Okay, we can do rotate off. It spins fast. Okay, and that's it. Okay, so this should be the image that I see from you guys. Okay, it should look like this for the end of this one. Okay, all right. So we're going to take a look at the next one. This is called Lysozyme, which is 2LYZ. Okay, and I'm going to pull this one up from the PDB. So I'm going to just do my own little thing so I can get this loaded. Here we go. Okay, so we're going to type in show info. Okay, and this gives us all the information on Lysozyme. Okay, so first we want to get rid of the water. So we're going to delete water. This is a lot of water surrounding that. Okay, and now I'm in a different orientation of the molecule here, but what we're going to do is we're going to click on Style and Scheme, and we're going to do CPK space fill. Boom. Beautiful. Okay, now why do we do space fill? This is when we want to get a good idea of the shape of the protein. Now if you look, Lysozyme has a very specific shape, and right here is this little V-shaped structure. That's the active site. Okay, and so we can see the active site right there. That's called a cleft. Okay, very often you'll see faces and clefts describing structures of proteins. That's a cleft, right? It's just a big groove. Okay, and so that's where lysozyme binds what's called a hexasaccharide and an inhibitor trinag, which allows it to interact. Okay, so we're going to go to wireframe. Okay, so let's refresh our scheme to wireframe. Okay, now we're going to type in these commands. Okay, so we're going to do SS bond 60. Okay, we're going to do backbone only. Now we want to show backbone. Do you see how the SS bonds popped up, yellow? Okay, so now we're going to go backbone only. Okay, and they're off. Now we're going to go backbone 80, making our backbone a little narrow. Okay, we're going to do SS bonds on. There they are, but they're not connected. We're going to make them a little thicker. Okay, and again, the numbers you play around with them. You can do 60, 50, 80, 100 is really thick. And then we're going to set SS bonds backbone because we want to connect them to the backbone. Okay. There we go. We got 4 SS bonds there. Okay, they're yellow, and I want to make the backbone 1 and the SS bonds 0.5. So let's go SS bonds. Backbone. There we go. Now we can see those are our disulfide bonds, which means they're being held together by cysteines. Okay, and you can see there are 4 of them there. Okay, and the pairs of cysteines involved. So zoom in and say, okay, this is 30 and 115, and this one is 6 and 127. Okay, so there's a lot of interaction between different parts of this protein to make it fold up. Okay, one thing I like to do with cysteines, select CYS is cysteine. I like the color in green so I can see. And look, the hydrogen bonds get colored green too, but those are the cysteines. Okay, and you can see that wherever a cysteine is, that's where they form a disulfide bridge. Okay, and that holds them together. All right, I'm going to undo what I just did. Okay, because I want to kind of stay in line with the tutorial. Okay, now we're going to do cartoon only. Okay. All right. We're going to do cartoon only. going to color structure. There we go. And our structure looks like what we have here in the image. Okay, pretty close to it if we do this. Okay, and there's a little 3/10 helix here. It's right here on the bottom. Okay, and so here's our 3/10 helix. So it's almost a complete helix. Okay, and that's purple. Okay, so how many helixes are there in here? You're going to count your helixes. You got 3 of them plus a 3/10, so 3 and 4. How many beta sheets do we have? 1, 2, 3, 4, 5. Yep. Okay. Now we want to see the sheets where they are in relationship to the cleft. So you can kind of see that the cleft is right about here. Okay, let me make this bigger so you can see this. Here's our cleft. It's right about here. Okay, and the sheets kind of form the floor of the cleft. So let's go ahead and follow the directions here. It says do space fill only. Now we can see the cleft with our sheets. Oh, look at that. See with the cleft, the sheet's right here, and it forms the bottom of that cleft. Okay, it creates the floor of the cleft. If we turn this, there's the floor of the cleft. Okay. All right, now we want to look at some hydrophobic stuff. Okay, so we're going to do CPK. So we're going to go color CPK. Okay, and now we're going to select hydrophobic. Make sure you type things correctly. We're going to color green. And then we're going to go select polar, color yellow. So now I can see the polar and non-polar regions, and look at that. Most of that cleft is hydrophobic on the bottom and hydrophilic on the top. It's polar on the top and non-polar on the bottom. So that must have something to do with the molecule that it's going to interact with. Okay. And so now we're going to look at the location of these. So we're going to type wireframe only. And this is for the polar residues. And we're going to do wireframe 100. So we can see now that there's a lot of green in here, which is hydrophobic. A lot of stuff that's hydrophobic in here. And then the polar stuff is the yellow. Okay, so now we can reverse this and we can say, okay, let's go to space fill. And we're going to select hydrophobic, wireframe only. And now what we've done, or if you make a mistake, you can always retype. The beauty of this, it's very forgiving. Now we can see the yellow, okay? And the yellow, again, is our polar residues. And we can see that most of this thing is polar, and then we got this non-polar hydrophobic stuff here. A lot of it's tucked in the middle. You notice that? Okay? So that's important because proteins exist mostly in a watery environment. So most of the polar stuff's on the outside. The non-polar stuff is tucked away on the inside. If I did this again, I'd probably use a different color like magenta or something to show up. Okay, so now we're going to select the protein. And we're going to do space fill only. Okay, and now we're going to do the slab command. So we're going to go slab on. This just allows you to see a cutaway of the protein. So if we do slab 50, we're cutting it in half. We're seeing it as if it was cut 50% of the way through. Okay, if we do slab 80, right, now we're doing a cutaway, and we're seeing 80% of the model is visible, and we're just cutting away a little bit of it. Okay, so that really gives you a different way to visualize the protein. Okay, so then we're going to do slab off. Again, take your time going through this. I'm moving along because my battery is going to die on my laptop soon. And then what we want to do is type select positive. This is showing our positively charged stuff. We're going to color that red. Select negative. We're going to color blue. Okay, so we can see the stuff that's positively and negatively charged. Okay, now the other stuff that's yellow, it's polar, but it's not a very strong interaction there. Okay, we can do polar that are not charged. So we're going to select. We're going to color that magenta. All right, and so those are our polar non-charged. This is our non-polar. And then these are our charged surfaces. So we can see that the active site, top of it is non-polar, bottom of it is polar and not charged, okay? And then we actually have a couple of charges in the middle there. And that's all going to help with this thing binding to its appropriate substrate, okay? Okay, and then the last thing we're going to do is we're going to look at beta sheets, okay? So we're going to select protein, and we're going to do wireframe only. We're going to color CPK. Set SS bonds side chain, select sheet and cartoon, and wireframe 50. Okay, and so what we're able to see here is the beta sheets, okay, and where they're embedded within the protein, okay, and that they go from the surface of the cleft and move away, okay. So you can definitely see the 3 strands of the polypeptides that are in the principal beta sheet here, right in here. So this lets us see what types of side chains are sticking out in the active site, okay, and how important those are, okay. So to make this a little easier, we can just type restrict sheet. So now all we're going to look at is the beta sheet, and we can see the amino acids in the beta sheet that are sticking out that play a role in how this thing interacts and catalyzes what it's supposed to do. If we want to look at just the hydrogen bonds, we can do H bonds, calculate. Okay, we're going to do background white because this looks better with a white background. We're going to do H bonds 40, cartoon off. We're going to color H bonds orange. Okay, and if we zoom in on this, you can see that it looks just like the image. Okay. Trying to move this. Doesn't want to move. Okay. But this is our, you can see our H bonds in here. Okay. And then we can also look at it in the beta sheet without looking at some other things. Just let's see. We're going to zoom in on the beta sheet and center it on our screen. So we shift and double click. All right, it's centered. All right, and then what we want to do is type restrict backbone. And now we can see what this looks like. So it looks like this image here. Okay. Excuse me. And so you can see how those hydrogen bonds interact with the backbone on the beta sheet. Okay, and that it's all this lateral bonding going on. Okay, and so the side chains are sticking out to the side, if you notice. Okay, the side chains stick out perpendicular, okay, with respect to the plane of the beta sheet. Okay, let's take a look at alpha helices. So we're going to select 5 to 14. We're going to do cartoon, and we're going to do wireframe 100. Okay, and we're going to turn H bonds on like we did before for the beta sheet. So if you don't remember how to do that, you can just look back up here and see H bonds calculate. And we'll do H bonds 40, and we're going to color H bonds something different. Let's see, what did I pick? Looks like I did magenta. There we go. Okay. So we have that on. Okay. So now we can see with the cartoon how that looks. Okay. Now we want to turn off the cartoon. Okay. And this looks a lot like the image that we have here. Okay. We still have a little piece of that there, right? And then what we want to do is zoom in. Okay. And you can see, okay, how those form those bonds. Okay. So you can pick any pair you want and just say, okay, so for example, here's number 6. Looks like it's interacting with number 10, right? 6 and 10. Yep. Okay. So just pick a couple of those and put them in there. Now, how many amino acid residues are part of the 2 residues in each pair? Well, if you kind of look at this, you'll see it's 1. Here's 1, 2, 3, 4. Okay. So they're about 4 apart. Okay. All right. So then we're going to select hydrophobic. Okay. And we're going to color green. There's our green ones. Okay. And if we take a look, and then color the polar ones, your favorite color. I like cyan. So I'm going to do select polar and color cyan. So I have green and cyan all over the place here. Okay, even in this chain I have them too. Okay, what's important here though is I'm looking at just my my helix. Okay, all right, and then let's see. Describe the distribution of the hydrophobic polar and polar side chains of the helix. Okay, so if you look at the helix, we notice that the polar ones are on the top and the bottom, and in the middle is the green one. Okay, and so now we're going to look at our 3/10 helix, and this will take us to the end. So we're going to select protein. Okay, we're going to do style scheme cartoon. H bonds off. And then what we're going to do is display only that particular helix. So we're going to do restrict 80 to 85. That allows us to only look at one portion, right? Residues 80 to 85. And then we're going to calculate and display the H bonds, right? So we're going to calculate H bonds, and then we're going to do H bonds 40. Okay, we're going to color them cyan because this way it's a little more of a contrast. We're going to do, we're going to center this on number 83. This way it's in the middle of our screen. And then we're going to do backbone 100. And finally turn off our cartoon. And there we go. We have our helix set up quite nicely. Okay, a couple of hydrogen bonds. One of the things we can do is we can set H bonds to the backbone. Okay, and now they're connected nicely. Okay, and if you look at the image, it looks just like what we have over here on the screen. Okay, so there we go. That's it. And if we rotate this upside down, we can look down the plane. We can just see our H bond showing. Okay, all right, and that's it. That's the tutorial. Okay, so again, go back through it, practice it. The whole idea is to get you familiar with how the system works. That's really what this is about. These images ultimately come from X-ray crystallography, and they are from proteins that were crystallized and analyzed using X-rays at a synchrotron light source. This was probably done at Brookhaven Labs synchrotron light source. I'd have to look up the information on it and see. But that's it. So keep trying. If you get stuck, just shoot me an email, text. I'll help you guys out. Don't get frustrated. And also, this is something that you should take your time doing. This whole assignment was not meant to be done in one day. Some of you guys, I know, were doing it one day and saying, "Oh my gosh, it took me 4 hours." Yeah, I gave you 2 weeks to do it, so I wanted you to spread it out. Because I know you have a lot of other work in your other classes. Okay, by no means do I want this to be this like overwhelming class that's taking up all your time. You could have spent a day on this JMol stuff and a data bank, and then spent another day, which is the equivalent of like a half an hour, 40 minutes on one protein and then doing another and another. Okay, so that was the idea I had behind that. But I hope you guys understand this a little bit better. I hope it makes sense. And as we move on, we're going to be looking at other proteins and just playing around with different ways to visualize them. Okay, and then we'll talk about them a little bit more. Okay, that's it. Good luck. See you soon.